All right, so today we're going to look at some problems that involve using vectors, and particularly we're going to look at working with vectors in component form, because component form is awesome and it's much easier to do operations on vectors that are in component form than in any other form. So first we're going to look at displacement vector. So here we have a situation, and the components, the three different components, the I, j, k, are really nice when we have anything in 3 dimensions, which is our world. Here we have the picture is only 2 dimensions, so we have our x and our y, and you have to imagine the 3rd dimension is coming out at you. And we have a hawk who really wants to know that if the top of the house is 30 feet high and the top of the tree is 45 feet high, we want to write the displacement vector from the top of the house to the top of the tree in component form. So we're kind of doing this right there, but also with height. And each scale is 10 feet. So if we think about where we are right here, and so the house itself is has a position vector of 20i plus 10j, and it has a height of 30 feet plus 30k, or shorthand mathematically, we use our little sort of triangular brackets, and we do 10, 20, 30. And then the top of the tree, so the tree is at 30i. I mean, if we think about the position vector itself to there, so it would be 30i plus, that is at 10, 20, 30, 30j, and it's up 45 feet, so 45k, which, much quicker notation, 30, 30, 45. So those are the position vectors. And what we want is the displacement vector, which is really what would you add to 20, 10, 30 to get 30, 30, 45? And the answer is in the x direction, right? This right here, that's 10. And in the y direction, that's going to be, oh, that 10, 20, 30, 40. Oops, that's a 40, not a 30. And so we're going to add 30 to get there. And then finally, vertically, we are going up 15. And so there's our displacement vector. Again, we could write that also as 10i plus 30j plus 15k. Now problem 2 is asking for, or the second half is find the magnitude of the displacement vector. So if this hawk was sitting on top of the house, how far would it fly if it flew in a direct line to the top of the tree? And this, in 3 dimensions, the distance between 2 points is very similar to in 2 dimensions, which would give us Pythagorean theorem with our components, but we just sort of do Pythagorean theorem on steroids, and we're going to say our x component squared plus our y component squared plus our k component squared, and we take the square root of all that, and you end up with an answer of 35 feet, which you could do on your calculator if you want. All right, next problem. So here we have 2 forces. Forces are also often represented by vectors. If you split up a force along a line into its horizontal and vertical parts, then it's much easier to add forces than it is to use the vectors in their angles. So because here, when you want to figure out what we need to do so that it's stationary, so if we're acting on this, our overall force, so the main force, it has an 8i and a 3i, so it's 11i, well, a force of 11 in the I direction, and then minus 6 plus 2 is going to be plus 4, oops, sorry, minus 4 in the j direction. And if I want my object to remain stationary, I have to directly counteract that. So I want some x component and some y component that would make 0, and they just need to be the opposite. So I want to do negative 11i and 4 in the j direction, and that vector will have the same magnitude but be pointing in exactly the opposite direction. So instead of, if I went 11 and negative 4, and I did this going -11 and 4 overall is that, and those are the same length but different different directions. Okay, here's another force problem. So a force is pushing an object in a direction of 50 degrees south of east. So let's put this on a coordinate system, sort of south of east. So if east is this way and we're going south, so this is 25 newtons and it's 50 degrees south of east. And then we have a second force pushing the object in a direction 70 degrees north of west. So west is out here, 70 degrees north of west means that right there is 70, and with a force of 60 newtons. And we want to know the magnitude and direction of the resultant vector. Now you could use some triangle, trig, law of sines or law of cosines more likely. However, I think the simplest way to do this is to split each vector into its components and then add the components and then go back to magnitude and angle. So, and to do all this, we're going to use our idea that if you have a vector of magnitude v and angle theta from the horizontal, then your x-coordinate right here, your I component, is going to be your magnitude cosine of theta, and your y component, your j component, is going to be your magnitude sine of theta, which is very similar to what we did with our polar coordinates. It's the same idea, only our magnitude of our vector was r. And in the real world, we are using degrees. One of the few times we're going to use degrees and not radians. So if I do this, my first vector right here, this vector, the x component is 25 cosine 50 in the I direction, and then we have 25 sine of 50 degrees in the j direction. My blue vector provides, well, this is my overall vector, let's just say that. So this is my vector. My blue vector is 70 cosine, oh wait, it's not 50 degrees. I need to come up with the actual angle from 0. So I could use -50, or I could use 310, which I think is easier. 310 degrees, because I want this angle. Because this works as long as we are from standard position. And so, oh, it's not 70 degrees, it's 60. Wow, I'm having a rough time on this video. So I have 60 newtons. Cosine of, that's going to be what, 110 degrees in the I direction. And I have 60 newtons times sine of 110 degrees in the j direction. And I can combine these into one vector, and I'm just going to add my I parts together and my j parts together. And we can do that with our calculator. And this one time you want to make sure you are in degree mode. And we're going to do 25 cosine of 310. We're going to add that to 60 cosine of 110. And I'm going to store that, because I'm going to use this later. I'm going to store it in alpha x, because that's my x quantity, sort of the magnitude in the x direction. And there's that answer. I'm going to do the same thing for my y's, and so I have 25 sine of 310 plus 60 sine of 110, and I'm going to store that in alpha y. I know this is going to be in my y. And so overall, my vector is 30, nope, what am I doing? So it's -4.452 in the I direction and 37.230 in the j direction. So overall, the force will be -4-ish this way, 37-ish that way. So my vector itself is more in that direction. But what I really want is the magnitude and the angle. So I'm coming up with this, and I want the magnitude of that vector. The magnitude, right, so this is my x-coordinate, this is my y-coordinate. The magnitude of my new resultant vector is going to be square root of x squared plus y squared. And the storing makes this super easy. So I'm going to say square root of alpha x squared plus alpha y squared. And my answer is 37.4956. So that's my magnitude. Newtons, and because I stored, I know I'm correct to 3 decimal places. Now my angle is going to be an inverse tan of my y value, alpha y, divided by my x value, because there's my picture, opposite over adjacent. And so negative 83, now that is definitely not the angle where I'm at, but that is my reference angle. So if I was at negative 83 and I add 180, which is what my theta, is what my standard position angle will be. So there's lots of ways you could talk about this. You could say it's 83 degrees north of west, or you could say, yeah, that would be strange to say 96 degrees because it's not directly north. So I think maybe actually that would be the best way to do it, 80 degrees north to west, or 96 degrees counterclockwise from east. All right, so let's try. So this is one of the things that you should be doing on your own. I want you to read page 662. It's going to talk about other uses for vectors in components. The 3 components work very well for 3 dimensions, but you can also use vectors to represent a series of quantities and trying to keep them in some sort of order, and then you can add and multiply to your vector and keep your sort of placeholders in their places. So you take a look at that, and then 19 and 20 will relate to that from your mastery, and you have other mastery on your sheet.